4.5 billion years ago, something the size of Mars hit the Earth so hard that a piece of it became the Moon. We know this. Science is pretty confident. But here's the part that quietly keeps planetary scientists up at night. When they measured the Moon's chemical fingerprint, its atomic signature, the thing that makes every object in the solar system uniquely identifiable, it matched Earth's. Perfectly. Not approximately. Not close enough. Perfectly. Every other rock in the solar system has its own identity, not the Moon, and that should be physically impossible. So either the physics is wrong, or something happened that we still don't fully understand, and honestly, it might be both. Which is exactly why, for the first time in over 50 years, we sent humans back toward the Moon, because the answer to this might be sitting in rocks no one has ever touched. Before we begin, if you are new and enjoy what I do here, make sure to hit like and subscribe so you don't miss where this story goes next. And I don't say this to be dramatic, but by the end of this video, the Moon is going to look fundamentally different to you than it does right now, in the best possible unsettling way. Now get cozy and let's ease into it. Part 1. The Perfect Crime in Space. 4.5 billion years ago, there was no Moon. There was just Earth. Barely Earth, really. More of a concept than a planet. A spinning ball of molten rock so hot that the surface wasn't solid, it was a global ocean of liquid stone glowing orange and red under a sky thick with debris. No continents, no oceans, no atmosphere worth mentioning. Just heat, chaos, and the constant percussion of incoming rocks slamming into a world that hadn't yet figured out what it wanted to be. The early solar system was nothing like the orderly place we live in today. Think of it less like a planetary system, and more like a demolition derby, where the vehicles are the size of continents, and the track is 300 million miles wide. Dozens of planet-sized objects called planetary embryos were careening through the inner solar system, colliding, merging, breaking apart, and colliding again. Gravity was the only rule, and gravity doesn't care about anything except mass. The biggest things pulled in the smaller things. The smaller things hit each other and made bigger things. It was violent on a scale that has no modern equivalent. Earth, in this picture, was already winning the size competition in its orbital neighbourhood. It had gathered enough mass to start pulling in everything nearby. But it wasn't alone. Sharing roughly the same orbital region, the same gravitational territory, was another object. Scientists call it Theia. It was approximately the size of Mars, which means it was roughly half the diameter of Earth and about 1/10 of Earth's mass. Not a small rock. A full-scale planet in its own right, with its own core, its own mantle, possibly even its own geological evolution already underway. And then, at some point in that first 100 million years of solar system history, Theia hit Earth. Not a head-on collision. The models suggest it was more of a glancing blow, an oblique impact at a shallow angle, the kind that maximizes the amount of material thrown outward, rather than simply absorbed. The energy released in that moment is almost impossible to hold in your mind. We're talking about an impact so powerful that both bodies were partially vaporized. Rock didn't just crack, it became gas. The surface of Earth, already molten, was blasted outward in a spray of superheated material that entered orbit around the surviving remnant of the planet. And from that orbiting disk of debris, cooling, clumping, gravitationally attracting itself into larger and larger pieces over the course of perhaps a few thousand to tens of thousands of years, the Moon assembled itself. This is the giant impact hypothesis. And for a long time, it felt like the answer. It explained things that were genuinely hard to explain otherwise. The Moon is unusually large for a natural satellite of a planet our size. Most moons are tiny compared to their host planets, but ours is about 1/4 of Earth's diameter, which is enormous in relative terms. The hypothesis explains that. It also explains why the Moon has relatively little iron. The iron from both Earth and Theia had already sunk to the cores of both planets before the impact, so the debris thrown into orbit was iron-poor mantle material. It explains the Moon's orbit, its angular momentum, the way it's tilted. When you line it all up, the giant impact hypothesis is elegant. It works mechanically. It fits the geometry. So scientists were satisfied. Mostly. Here's the problem, and this is the thing that, once you understand it, you cannot ununderstand. If the moon formed from a collision between two separate planets, then the moon should look chemically like a mixture of both planets. Earth material plus Theia material, blended in some proportion, producing a moon with a distinct chemical identity, similar to Earth's but measurably different. That's not just an expectation, that's physics. Two objects with different chemical histories slamming together cannot produce a third object that is chemically identical to just one of them. But that's exactly what happened. When scientists analysed lunar rocks, first brought back by Apollo astronauts beginning in 1969, and then studied with increasing precision for the 5 decades that followed, they found something that didn't fit. The moon's chemical fingerprint matched Earth's. Not approximately, not within a reasonable margin of error. It matched almost perfectly, at a level of precision that goes down to the atomic scale. And here's why that's strange. Every object in the solar system has its own unique chemical signature, built into it during formation from the particular mix of materials present at its specific location and time. Mars has its signature, the asteroid Vesta has its signature, meteorites from across the solar system each carry their own. The solar system is full of chemically distinct objects, and you can tell them apart even from tiny samples by measuring the ratios of certain atomic variations locked inside them. The moon should have its own signature too, a mixture of Earth and Theia. Instead, it looks like it was built entirely from Earth. That's not just unexpected, that's a mystery. A forensic crime scene where the foreign suspect left no fingerprints at all, despite being required by every physical model to have been there. And it's a mystery that Planetary scientists have been trying to solve without complete success, ever since. The question isn't just where the moon came from. The question is how the moon can exist in its current chemical state without breaking the physics of planetary formation. And that question, it turns out, runs far deeper than anyone initially realized. Part 2. The fingerprint that should not match. To understand why scientists found this so disturbing, you need to understand what a chemical fingerprint actually is. Every element in the periodic table exists in slightly different versions. Atoms with the same number of protons but different numbers of neutrons. These are called isotopes. Oxygen, for example, comes in 3 stable isotopic forms: oxygen 16, oxygen 17, and oxygen 18. The ratios of these 3 forms in any given rock depend on the conditions under which the rock formed, the temperature, the pressure, the specific mix of stellar material present at that location in the early solar system. Different places in the solar nebula had different isotopic ratios. Different planets formed from different patches of that nebula. So every planet ends up with its own characteristic isotopic fingerprint, baked into it at the atomic level. This isn't a subtle effect. The differences between planetary bodies are real and measurable, and they have been measured thousands of times across hundreds of different samples. Mars has its own oxygen isotope signature. You can take a rock that landed on Earth as a meteorite, measure its oxygen isotopes, and know immediately whether it came from Mars. The asteroid Vesta has its own signature, distinct from Mars, distinct from Earth. Ordinary chondrite meteorites, the most common type of space rock, have their signature. Enstatite chondrites have theirs. Every category of solar system material has a characteristic ratio that tells you where it came from, the way an accent tells you roughly where someone grew up. Earth has its oxygen isotope signature. And every rock from the moon, every single sample ever brought back, across 6 Apollo missions and dozens of kilograms of material, has the same oxygen isotope signature as Earth. Not similar, not close, the same. When scientists first noticed this, they assumed it was measurement error. Instruments in the 1970s weren't as precise as they are today. Maybe the difference was there, just too small to detect. So they waited. The instruments got better. Mass spectrometry improved by orders of magnitude. By the 1990s and 2000s, scientists could measure oxygen isotope ratios to a precision of a few parts per million, and the answer kept coming back the same: Earth and Moon match. Then they checked other elements just to make sure oxygen wasn't a fluke. Titanium isotopes. Same story, Earth and Moon are nearly indistinguishable, while other solar system bodies diverge measurably. Chromium isotopes. Again, the Moon tracks Earth rather than showing any sign of a foreign contribution. Tungsten isotopes, which are particularly useful because they're sensitive to the very early differentiation events in a planet's history. The Moon and Earth show the same patterns in ways that continue to puzzle researchers even today. The more elements scientists checked, the more the same conclusion emerged. The Moon does not chemically behave like an object that contains material from a foreign planet. And this is where the paradox becomes almost absurd, because the giant impact hypothesis doesn't just say Theia contributed a little material. The simulations, which have been run thousands of times with increasingly sophisticated models, consistently show that somewhere between 40 and 70% of the Moon's mass should have come from Theia. Nearly half the Moon in most models. Some models push that number even higher. Think about what that means. If you had a bowl of red paint and a bowl of blue paint, and you poured them together, you would get purple paint. You would not get red paint. The mixture has to show both components, in proportion to how much of each you added. If you added 60% blue and 40% red, the result should be measurably different from pure red. The Moon is red paint. Statistically, the odds of two independently formed planetary bodies, born in different parts of the solar system, even if relatively close to each other, having identical isotopic ratios across multiple elements, are extraordinarily small. Scientists have calculated these probabilities, and while the exact numbers depend on assumptions about how similar Theia's formation environment was to Earth's, the general conclusion is that this level of chemical identity goes well beyond what random chance should produce. This is what researchers began calling the isotopic crisis in lunar science. Not a problem at the edges of the model, a crack running through the centre of it. The Apollo missions were supposed to solve the mystery of the Moon's origin. They returned with rocks, and those rocks confirmed the giant impact story in some ways, and quietly, systematically dismantled it in others. Because here's the thing that makes this more than just a scientific puzzle. What the isotopes are really telling you is something about identity. They're telling you that the Moon doesn't know it came from somewhere else. Every atom in every lunar rock is pointing back at Earth, as though the Moon has no memory of Theia at all. A planet the size of Mars hit our world at tens of thousands of miles per hour, and the object that formed from the aftermath is chemically indistinguishable from the Earth that got hit. Either something erased Theia's contribution completely, or Theia wasn't really that different from Earth to begin with, which creates an entirely different set of problems. Either way, the Moon is carrying a secret in its atomic structure, and that secret is pointing at something fundamentally incomplete in our understanding of how planets form. The question of where Theia went and why it left no trace is about to get considerably stranger. Part 3. The Missing Planet Problem. Let's stay with Theia for a moment, because Theia is one of the most peculiar objects in the history of planetary science. A planet that we know must have existed, that we have no direct evidence for, and that seems to have vanished so completely that even the Moon it helped create doesn't remember it. Every simulation of Moon formation that scientists have run requires Theia. You cannot get the Moon to form, at its current size, in its current orbit, with its current angular momentum without a large impactor. The physics demands it. You need something big hitting early Earth from the right angle, at roughly the right speed to throw enough material into orbit to build the Moon. A Mars-sized planet is the standard answer, and thousands of computational models have converged on something in that size range as the necessary ingredient. So Theia had to exist. There's no getting around it. But here's the problem. If Theia existed, and if Theia hit Earth, and if 40 to 70% of the Moon came from Theia, then where is the chemical evidence of Theia in the lunar rocks? Not a trace. Not a whisper. Every element measured, every isotopic ratio checked, every comparison made between Moon and Earth comes back pointing to Earth alone. Theia, as a chemically distinct entity, appears to have been erased so completely that it might as well never have existed. One possible explanation, the one that planetary scientists have spent the most time exploring, is that Theia and Earth were actually formed from very similar material in the first place. If both planets assembled from the same patch of the early solar nebula, sharing the same isotopic inventory from the start, then their identical fingerprints in the Moon wouldn't be a mystery at all. It would just mean the two bodies were chemically twins before they ever collided. This sounds neat, but it creates its own problems. The early solar system was not a quiet, well-mixed environment. Material from different radial distances, different distances from the Sun, had different isotopic compositions. Objects that formed at the same orbital distance would have similar compositions, but the degree of similarity required to explain the Moon's isotopic identity is extreme. Earth and Theia would have had to be almost perfectly matched across multiple independent elemental systems simultaneously. While not impossible, it requires either a remarkable coincidence or a degree of radial mixing in the early solar nebula that isn't well supported by current models of solar system formation. There's another wrinkle. The absence of Theia's signature isn't just about the Moon, it's also about what we don't find in meteorites. If Theia was a large differentiated planet, meaning it had a core, a mantle and a crust, which it almost certainly did given its size, then its disruption during the giant impact should have scattered some of its material throughout the inner solar system. Some of that material should have ended up as meteorites eventually reaching Earth, and yet no meteorite type in our collection has been definitively identified as Theia debris. The asteroid belt, which preserves a partial record of early solar system bodies, doesn't seem to contain a clear Theia signature either. Theia is missing everywhere. Not just in the Moon, everywhere. This is the missing planet problem, and it has no clean resolution yet. The options on the table range from the mundane to the exotic. Maybe Theia really was isotopically identical to Earth, and the coincidence, while unlikely, is simply what happened. Maybe there was some process, either during the impact itself or in the immediate aftermath, that so thoroughly homogenized the material from both bodies that Theia's signature was completely buried. Maybe some of the models about how much of the Moon came from Theia are simply wrong, and the real number is much lower than simulations suggest. Maybe all of the above are partially true. What none of these explanations does is fully satisfy the data. Each one requires some degree of special pleading, some assumption that's uncomfortable, some coincidence that strains credibility, some process that hasn't been convincingly demonstrated. The Moon, sitting 250,000 miles above our heads, reflecting enough sunlight to cast shadows, is built from material that science cannot fully account for. And what's particularly unsettling is that this isn't a small gap in our knowledge. It sits at the very centre of the origin story, the moment that created the Earth-Moon system, shaped the conditions for life on Earth, and set the trajectory for everything that followed. The model that was supposed to explain how the Moon got here cannot explain what the Moon is made of, and when scientists went looking for better models, they found something that made the problem considerably more complicated. Part 4. The giant impact model starts to fail. The giant impact hypothesis didn't become the dominant theory by accident. It earned that position by explaining things that other theories couldn't. Before the giant impact model came along in the 1970s and 80s, there were three main competing ideas for how the Moon formed. The first was fission, the idea that early Earth was spinning so fast that a chunk of it broke off and became the Moon. The second was capture, the idea that the Moon formed somewhere else in the solar system and was gravitationally captured by Earth. The third was co-accretion, the idea that Earth and Moon simply formed together from the same cloud of material, growing side by side. Each of these theories had some appeal, and each of them had fatal problems. Fission required Earth to have been spinning impossibly fast. Capture requires a level of orbital precision that's essentially impossible to achieve without some mechanism to slow the captured object into a stable orbit, and no one had a convincing one. Co-accretion couldn't easily explain why the Moon has so much less iron than Earth, since both would have formed from the same material in the same proportions. The giant impact hypothesis threaded all these needles at once. It explained the Moon's size, its iron depletion, its angular momentum, and the Earth-Moon system's total rotational energy in a single coherent framework. That's enormously powerful in science. When one model explains multiple independent observations simultaneously, it earns serious credibility. So the physics of the model, the geometry of the impact, the formation of the debris disk, the accretion of the Moon from that disk, those parts of the story are genuinely solid. Angular momentum is conserved. The simulations show you can get a large Moon in a reasonable orbital configuration. That part works. The problem is the chemistry. And the chemistry problem is not a minor adjustment issue. It goes to the core of what the simulations are doing. Here's what the simulations actually show when you set them up with standard parameters: a Mars-sized impactor, a glancing blow, an Earth of the right mass. You get a debris disk. That disk is made up of roughly 70 to 80% Theia material in most simulation runs. The reason for this is geometry. The impactor's outer layers and mantle are the parts most easily ejected into orbit, while much of Earth's material stays bound to the surviving planet. So the Moon that forms from this disk should be predominantly Theia, not Earth. But the Moon is not predominantly Theia. The Moon is, isotopically, essentially pure Earth. Scientists spent years trying to find a version of the standard impact simulation that could reproduce the isotopic data. They adjusted the angle of impact, changed the mass of the impactor, varied the speed, tweaked the initial spin of Earth. In each case, the dynamics would change, sometimes dramatically, but the fundamental chemical composition of the resulting disk remained dominated by impactor material. You simply cannot design a simple glancing blow impact between two chemically distinct bodies and get a Moon that looks like only one of them. The chemical memory problem is what some researchers began calling this. The material in the disk remembers where it came from. Theia's atoms carry Theia's isotopic signature, and no amount of mixing in a debris disk is going to erase that, because the mixing in a traditional impact scenario doesn't go down to the atomic level. Rocks mixing with other rocks don't exchange isotopes. You'd need something far more extreme than that. This is the point where the giant impact hypothesis, as originally formulated, genuinely starts to show its age. It remains the best framework. There's nothing else that comes close to explaining the Moon's existence as well. But it requires modification, possibly radical modification, to account for what the lunar samples are actually telling us. And that search for modifications has produced some of the most creative and controversial ideas in planetary science. The question is not whether there was a giant impact. Almost certainly there was. The question is what kind of impact, under what conditions, could produce a Moon that looks the way the Moon looks. And when researchers started seriously exploring that question, one of the first places they went was to a state of matter that most people have never heard of. Part 5. The synestia hypothesis. Imagine the entire Earth turned into a cloud. Not a cloud of water vapour, a cloud of rock vapour, spinning so fast and so hot that the concept of a solid surface becomes meaningless. There is no ground. There is no distinct planet. There is just a vast, rapidly rotating mass of superheated vaporized rock, extending far beyond where Earth's surface used to be, shaped something like a donut or a thick spinning disk, with the densest material concentrated toward the center and a diffuse vapor envelope extending outward. This is a synestia. The word comes from the Greek prefix syn, meaning together, and Hestia, the Greek goddess of the hearth and architecture of the home, the idea being that this object represents the shared structure of what would eventually become both Earth and Moon. It was proposed in 2017 by Sarah Stewart at the University of California, Davis, and Simon Locke at Harvard, and it represents one of the most dramatic reimaginings of early Earth in the history of planetary science. The central idea is this: if the giant impact that formed the Moon was significantly more energetic than the standard models assume, not just a glancing blow from a Mars-sized object, but a higher energy, higher angular momentum collision, possibly from a larger impactor or at a higher velocity, then the aftermath wouldn't have been a molten Earth with a debris disk in orbit. The aftermath would have been something different in kind, not just in degree. At sufficiently high energies, both Earth and Theia don't just melt, they vaporize. And the vaporized material from both bodies, now at temperatures of several thousand degrees and pressures far beyond anything we experience on Earth's surface today, would mix together at the molecular and atomic level in a way that simple liquid mixing never could. This is the key to why the synestia model is so attractive from an isotopic standpoint. In a superheated vapor, where everything is broken down into individual atoms and molecules, there's no Earth material and Theia material anymore. There's just material. Atoms from Theia mix with atoms from Earth in the vapor phase, and when everything eventually cools and condenses, the resulting objects, both the reformed Earth and the Moon, assembling within the vapor envelope, inherit the same mixed isotopic signature. The chemical memory is erased not by mixing rocks, but by vaporizing them completely. If this happened, the Moon wouldn't just look like Earth. It would be made from the same atomic soup as Earth, because for a brief period, Earth and Theia ceased to exist as separate entities and became a single superheated structure. The Moon would essentially crystallize out of a shared reservoir of planetary material, carrying the same isotopic fingerprint because it literally came from the same place at the atomic level. It's an extraordinary idea, and it has serious scientific backing, the thermodynamics work, the physics is consistent, and several research groups have developed simulations supporting the basic picture. The challenge is that it requires a more energetic impact than the standard model uses, which means a somewhat different set of initial conditions. The angular momentum of the Earth-Moon system today constrains how much energy could have been involved, and the synestia scenario requires mechanisms to shed some of that angular momentum after the Moon forms, possibly through a resonance interaction with the Sun called the evection resonance, which has been proposed but remains a topic of active debate. What the synestia hypothesis does beautifully is show that the isotopic identity problem is not necessarily fatal to the giant impact framework. It just requires the impact to have been more extreme than originally imagined. Instead of a collision that vaporized some rock, a collision that vaporized essentially everything. Instead of two planets merging with a debris disk, two planets becoming one shared vapor structure and then separating again into two distinct objects. The Moon, in this picture, isn't a chip off the old block. It's a crystal that formed when the old block melted entirely and then slowly resolidified. And Earth, sitting at the center of that ancient vapor cloud, is the remnant of the same process, rebuilt from the same materials, carrying the same signature, the synestia's larger child. But this model has competitors, and one of them approaches the same problem from a completely different direction, replacing one catastrophic event with something even more chaotic. Part 6. The multiple impact theory. What if the Moon wasn't born from a single catastrophic collision, but from a long sequence of smaller repeated accidents, a kind of slow accumulation of chaos instead of one defining moment? That is the core intuition behind the multiple impact hypothesis. Instead of imagining the early Earth as a one-time victim of a planet-scale collision, it treats it more like a planet under constant bombardment, slowly building its satellite from the leftovers of countless smaller events. Not a single dramatic origin story, but a process, messy, repetitive, and spread across millions of years. To understand why this idea even exists, you have to picture the early solar system not as the calm, structured environment we see today, but as something closer to a crowded demolition zone. Planetary embryos were still growing, orbits were unstable, collisions were routine, not exceptional. Earth did not form in isolation and then get hit once by a rogue planet. It formed in a crowd surrounded by hundreds of competing bodies, all exchanging energy, mass, and momentum in unpredictable ways. In that environment, impacts weren't rare events, they were a defining feature of planetary growth. Some were small enough to leave only craters, others were large enough to strip atmosphere, melt crust, or throw debris into orbit. The multiple impact hypothesis leans heavily on this reality. If every significant impact can loft material above escape velocity, then over time Earth could be surrounded by a growing cloud of ejecta. At first, this sounds almost elegant. Instead of requiring one improbably precise collision that produces the right amount of debris, in the right orbit, with the right chemistry, you let nature take many attempts. Each impact contributes a fraction of the material. Each collision adds a layer of complexity. Eventually, that accumulated debris settles into a disk, and from that disk, a moon gradually forms. In this view, the moon is not the child of a single violent event. It is the result of repeated inheritance, and this is where the isotopic problem becomes interesting again. Because one of the strangest things about the Earth-Moon system is not just that the moon exists, but that it so closely resembles Earth chemically. Oxygen isotopes, titanium ratios, silicon signatures, all nearly identical within extremely tight margins. Under a multiple impact scenario, that similarity becomes less mysterious in principle. If every impactor in the early solar system carried slightly different isotopic accents, then averaging over many contributors could, in theory, smooth those differences out. It's a bit like blending pigments. If you mix thousands of slightly different shades of blue, the result converges toward a uniform tone. No single source dominates. The final color becomes a statistical outcome rather than a fingerprint of any individual input. Now extend that idea to Earth itself. Earth is not a passive recipient in this process. It is also being struck repeatedly, absorbing and redistributing material from the same population of impactors. Over time, both Earth and the growing lunar disk are sampling from the same reservoir of building blocks. If that reservoir is already chemically well mixed at a solar system scale, then convergence becomes even more plausible. This is the main appeal of the multiple impact hypothesis. It turns a precision problem into a statistical one. Instead of needing a single perfectly tuned event, it allows for many imperfect ones that average out over time. But the moment you try to scale that idea into something physically complete, the difficulties begin to surface. The first problem is one of mass and efficiency. The moon is not small, it is large enough that building it requires an extraordinary amount of material to be placed into stable orbit around Earth. Small impacts are not particularly efficient at doing this. Most ejecta either fails to reach orbital velocity or ends up reaccreting onto Earth almost immediately. To accumulate lunar-scale mass, you either need an enormous number of small impacts, far more than typical early solar system models comfortably provide, or you need a smaller number of large impacts, which starts to resemble the very single impact scenario the hypothesis was meant to avoid. So the model begins to tighten on itself. The more realistic you make the impact sizes, the more you drift back toward a dominant event. The more you reduce impact sizes, the harder it becomes to accumulate enough material. Then there is the problem of orbital coherence. Even if you succeed in launching large quantities of debris into space over time, that debris does not naturally behave like a single system. Each impact produces material with different velocities, different directions, different angular momenta. Some of it escapes, some of it falls back, some of it enters highly eccentric or inclined orbits. To form a moon, all of this material must somehow settle into a relatively thin, stable disk around Earth. That disk must then cool, flatten, and accrete into a single body with a consistent orbit. In simulations, this is one of the hardest steps to reproduce under multi-impact conditions. Instead of a clean disk, you often get a chaotic environment, overlapping streams of debris, transient clumps, and unstable structures that do not easily coalesce into a single large satellite. Even when simulations do produce moon-like outcomes, they tend to rely on specific assumptions about timing, impact distribution, and material behavior that are difficult to justify as natural outcomes of early solar system dynamics. In other words, the model can work, but only under carefully tuned conditions. And this brings us back to the isotopic issue, where the hypothesis is supposed to shine. because even if multiple impacts can, in principle, average out chemical differences, that averaging has to happen in a very controlled way. If one or two large impactors dominate the mass budget, their signatures should still be visible. If the timing between impacts is too long, the system resets instead of accumulating. If mixing is incomplete, heterogeneity should remain. Yet the Moon does not show obvious signs of layered chemical diversity that you might expect from a strongly multi-source origin. Instead, it shows remarkable uniformity. That uniformity is both the strength and the weakness of all extended formation models. It demands extreme mixing efficiency, but the physical pathways to achieve that efficiency are still not fully convincing. So the multiple impact hypothesis ends up in a familiar place in planetary science, not rejected, but constrained. It is a possible contributor to lunar formation, perhaps even a partial explanation, but not yet a complete replacement for the giant impact framework. It softens some edges of the problem while sharpening others, and when you step back, a pattern begins to emerge across all these competing ideas, whether single impact, multiple impact, synestia models, or hybrid scenarios. Each one is fundamentally trying to solve the same riddle. How do you erase the chemical memory of distinct planetary bodies while still producing a physically stable moon? Each model reaches for a different kind of extremity. One requires a singular, perfectly tuned collision. Another requires prolonged statistical averaging across many events. Another requires a temporary physical state where boundaries between planet and disk disappear entirely. But all of them share one underlying assumption, that early Earth had to undergo a level of mixing so intense that traditional planetary boundaries stopped behaving normally. And every time these models are pushed to match the precision of the isotopic data, something subtle happens. They begin to strain, not collapse, just fall short at the edges. A mismatch in timing here, a mass deficit there, a mixing efficiency that is just a little too high to be physically comfortable. That is what makes the Moon such a stubborn problem. It is not that we lack explanations, it is that we have too many explanations that almost work. So when planetary scientists step back from the models, a quiet shift happens in the direction of inquiry. Instead of only asking how the Moon formed from above, from impacts and disks and orbital dynamics, they also begin asking what was preserved below. Because if the Moon is refusing to reveal its origin cleanly, then maybe the answer is not only in the sky above Earth, but in the planet beneath it. And that is where the story turns. Part 7. The hidden mixing problem. There's one more class of explanation that doesn't try to fix the isotopic problem at the moment of impact at all. Instead, it shifts the entire timeline forward and asks a more uncomfortable question. What if the Moon and Earth didn't start identical, but became identical? In other words, maybe the real action wasn't just in the collision itself, but in the long aftermath that followed it. To understand why this idea even has traction, you have to picture the early Earth-Moon system, not as two calm, separate spheres orbiting neatly in space, but as something closer to a violently unstable, glowing two-body system suspended inside a shared envelope of heat and debris. Earth at that time was not the familiar blue planet we know today. It was likely wrapped in a global magma ocean, a planet-scale layer of molten rock, potentially hundreds or even thousands of kilometers deep. The surface, if you could call it that, was not solid ground, but a churning interface between liquid rock and a thick, superheated atmosphere of vaporized material. The Moon, forming from the impact debris, was not a cool grey orb either. It too would have been largely molten, its surface continuously reshaped by heat, accretion, and gravitational energy. In its earlier stage, it may have resembled a glowing sphere of magma surrounded by a thin atmosphere of rock vapour. Now shrink the distance between them. At the time of formation, the Moon was likely far closer to Earth than it is today, not at its current orbital distance of roughly 30 Earth radii, but perhaps only a few Earth radii away. In that configuration, the system would have looked less like planet plus moon, and more like a tightly bound pair embedded in a shared thermal environment. And in that environment, distance stops meaning what it means today. Gravity becomes extreme. Tidal forces are not gentle ocean bulges, but planet-scale distortions that flex and heat both bodies. Radiation is intense enough that the space between Earth and Moon is not empty at all. It is filled with streams of hot vapor, ejecta, and partially ionized rock particles moving back and forth in complex trajectories. This is where the vapor exchange idea enters the conversation. If both bodies are partially molten and partially vaporized, and if the space between them is filled with energetic material, then it is physically reasonable to imagine that some fraction of material could be exchanged between Earth and Moon. Not in a slow, passive way, but in violent, chaotic cycles of ejection and reaccretion. Think of it less like two isolated planets exchanging atoms, and more like two connected reservoirs sloshing material back and forth through a turbulent channel. In this picture, Earth might lose vaporized silicates from its outer magma ocean, some of which enter lunar orbit and are incorporated into the forming Moon. At the same time, lunar material, still hot, still partially molten, could be stripped away and fall back onto Earth. Over time, this back and forth could, in principle, blur the chemical differences between the two bodies. This is the core intuition behind the equilibration models, that the Earth-Moon system, in its earliest phase, functioned as a chemically connected environment rather than two isolated worlds. And in broad terms, that intuition is not wrong. Simulations do show that some level of exchange is unavoidable in such an extreme environment. The physics of vaporized rock, coupled with strong gravitational coupling and close orbital separation, guarantees at least partial mixing of surface layers. Material does move, chemistry does interact, the system is not closed, but the critical question is scale. Because isotopic identity is not a surface phenomenon, it reflects bulk composition, the integrated history of an entire planet, not just its outermost layers. And this is where the vapor exchange model runs into a hard boundary. The exchange appears to be shallow relative to the depth of the magma oceans. Most of the material being shuffled between Earth and Moon comes from upper layers, the most accessible, most easily vaporized portions of each body. Meanwhile, the deeper reservoirs, where much of the mass and isotopic signature is locked, remain largely insulated. So even if you allow for a vigorous early period of material exchange, the math struggles to erase a deep compositional difference that should have been inherited from the original impactors. It is a bit like trying to homogenize two very different batters by repeatedly exchanging spoonfuls from their surfaces. You will eventually blur the top layer, but unless you can stir the entire volume, the deeper structure remains distinct. And that is the tension that persists across all these models. The physics consistently produces some mixing, but the isotopic data demands near total homogenization, not partial, not surface level, near complete. So once again, the model does something important. It captures a real process that almost certainly happened. The early Earth-Moon system almost certainly did exchange material. There almost certainly was a phase of intense thermal and chemical interaction. But the model struggles when asked to turn that partial effect into a complete explanation. And so the same pattern repeats, just in a different form. A mechanism is identified, it helps, it reduces the gap, but it doesn't close it. At this point, if you zoom out across all the major proposals, single giant impact, multiple impacts, synestia-like states, vapor equilibration after formation, a strange symmetry appears. Every model is trying to solve the same core paradox. How do you take two distinct planetary bodies, formed in different regions of a chaotic early solar system, and end up with two objects that are chemically almost indistinguishable? Each model answers by pushing the system toward extremes. One requires an impact so energetic that it melts and vaporizes most of a planet. Another requires a long sequence of collisions that statistically average out chemical differences. Another requires a temporary physical state in which Earth and Moon are not really separate objects at all. and another relies on prolonged post-formation exchange in a shared thermal environment. All of them are physically motivated. All of them are grounded in real processes we understand. And all of them share the same underlying strategy: increase the level of mixing until differences disappear. But the data remains stubborn, because isotopic similarity between Earth and Moon is not just close. It is exceptionally tight across multiple systems: oxygen, titanium, silicon, and others, often matching at levels that are difficult to reconcile with even the most aggressive mixing scenarios, unless something about the early system was fundamentally different from our default assumptions. So scientists begin to widen the scope again. If the impact didn't fully homogenize things, and post-impact exchange didn't fully erase differences, then maybe the starting assumption is incomplete. Maybe Earth and Theia were not as different as we imagine. Maybe they formed from a chemically narrow region of the solar nebula, already biased towards similar isotopic compositions. Or maybe the Earth-Moon system is sampling a portion of the mantle that is itself not representative of the original impactor mixture. And this is where the story takes a quieter, deeper turn, away from the sky and into the Earth itself. Because there is another possibility that has gained attention, not as a final answer, but as a complicating factor. Some of the material from the impactor may still exist, not on the Moon and not on the surface of Earth, but deep in the mantle. Hidden reservoirs near the base of the mantle, massive dense structures known from seismic imaging may preserve ancient, chemically distinct material. If parts of the impactor were not fully mixed into the Earth-Moon system, they may have sunk downward, accumulating at depth and remaining isolated for billions of years. In that case, the isotopic story is not erased. It is distributed. The Moon would represent one end of the system, the mantle reservoirs another, and Earth's surface would be just a thin, processed layer sitting above a much more complex interior archive, which leads to a final, unsettling implication. We may not yet know what Earth-like composition truly means in a planetary sense. We may be measuring a surface that has already been chemically rewritten by its own formation history, and if that is true, then the Moon is not just a record of what hit Earth. It is also a mirror of what Earth became after being hit. So where does that leave the isotopic crisis? Exactly where it has always been, unresolved but not directionless. Every mechanism we have explored, from violent impact to slow accumulation to atmospheric equilibration, contributes part of the truth. None of them fully explains the whole picture, but together they define the boundaries of what any successful theory must eventually satisfy. The Moon's origin is not a missing answer, it is a narrowing problem. Each new model removes one possibility and tightens the constraints on the next, and somewhere inside those constraints, in the chemistry of ancient lunar rocks, or in the deepest structures of Earth's mantle, or in samples we have not yet retrieved, the remaining pieces of the story are still waiting to align. Not with certainty yet, but with enough clarity to finally stop guessing. Part 8. The hidden structures beneath Earth. Somewhere beneath your feet right now, far beneath the ground, far beneath the deepest mine, far beneath even the deepest earthquake that has ever been recorded, there are two enormous structures that don't behave like the rest of Earth's interior. They sit at the base of the mantle, approximately 2,900 kilometers below the surface, resting on top of Earth's outer core. Each one is roughly the size of a continent. Some estimates suggest they span an area comparable to the Pacific Ocean in their lateral extent, while reaching several hundred kilometers in height above the core mantle boundary. They are not made of the same material as the surrounding mantle. They are denser, hotter, and chemically distinct in ways that seismic measurements consistently confirm. One sits beneath the African continent, spanning a huge swathe of the deep mantle under that region. The other sits beneath the Pacific Ocean. Scientists call them Large Low Shear Velocity Provinces, or LLSVPs, which is one of those scientific acronyms that perfectly captures how you feel when you discover that Earth contains continent-sized alien structures in its interior and you don't know what they are. The name refers to how they were discovered. Seismic waves generated by earthquakes travel through Earth's interior, and the speed at which they travel depends on the properties of the material they pass through. When seismic waves pass through these two structures, they slow down noticeably. The shear velocity, a particular type of wave propagation, is measurably lower than in the surrounding mantle rock. That velocity anomaly, mapped out over decades of earthquake monitoring using seismometers on every continent, revealed the existence of two enormous blobs of anomalous material sitting at Earth's base. And here's the first thing worth sitting with. We didn't find these structures by drilling down and looking at them. We found them the same way a doctor finds a tumour, by sending something through the body and watching how it behaves differently when it hits something it wasn't expecting. Every major earthquake that rattles the planet sends seismic waves radiating outward in every direction, passing through thousands of kilometers of rock before emerging on the other side of the world at a seismometer station. Scientists have been collecting those readings for over a century now, from stations on every continent, building up a picture of Earth's interior the way you might build a picture of a sealed room by listening to how sound bounces around inside it. And when they assembled that picture carefully enough, these two structures appeared, sitting there, enormous, unexplained, patient. They are ancient. That much seems certain from the evidence. The pattern of their influence on surface geology, through their effects on mantle convection, and the behaviour of hot material rising from the deep mantle, suggest that they have been in roughly their current positions for a very long time. Some estimates, based on geological reconstructions and mantle flow models, suggest they may be primordial, dating back to the earliest period of Earth's history, possibly to the time of the giant impact itself, which, if true, means these structures have been sitting undisturbed at the base of the mantle for 4.5 billion years, through the formation of the continents above them, through hundreds of millions of years of plate tectonics rearranging the surface of the planet, through the entire history of life on Earth, just sitting there, in the dark, at the bottom of the world. Their exact composition is unknown. No one has ever sampled them directly, and no instrument exists that could do so. What we know about them comes entirely from seismology, the study of how vibrations pass through Earth's interior, and from geochemical signatures in volcanic rocks that appear to tap into the deep mantle in their vicinity. Certain volcanic hotspots on the surface, places like Iceland, Hawaii, and the Canary Islands, appear to draw their material from unusually deep sources, plumes of hot rock rising all the way from the base of the mantle, and the chemical signatures in those lavas carry isotopic ratios that look subtly but measurably different from the rest of the mantle, different in ways that suggest the material down there has a distinct history, a history that doesn't quite match the story of the rest of Earth's interior. Those signatures suggest that the material in the LLS-VPS is different in isotopic composition from the surrounding mantle, enriched in certain elements and ratios that point to a different origin history. Not just old, different. Like finding a pocket in a well-mixed batter where the ingredients never quite blended in. After 4.5 billion years of a mantle that has been slowly, grinding, convecting, churning like an almost impossibly slow lava lamp, something in those two regions resisted the mixing. Something held together when everything around it didn't. That is, scientifically speaking, deeply weird. And it's the kind of weird that tends to point somewhere interesting. This is where the connection back to the moon's origin story starts to take shape. Because the LLS-VPs are not just a curiosity of Earth's interior, they're a potential archive of Earth's earliest history, possibly preserving material from a time before the giant impact, or, and this is the idea that has genuinely electrified some corners of planetary science, preserving material from the impactor itself. Think about what that would mean. In 2023, a research team led by Qian Yuan at Caltech published a paper making exactly this argument. The proposal was straightforward in its logic, even if the implications are staggering. When Theia hit the early Earth, most of the debris was redistributed, some of it thrown into orbit to form the Moon, some absorbed into Earth's bulk, some lost to space entirely. But Theia was not just a random rock. It was a fully differentiated planet. It had a core, a mantle, a crust. It had been cooking for tens of millions of years, separating its materials by density just like Earth had. And Theia's mantle, particularly its deeper, denser portions, may not have mixed cleanly into Earth's mantle during the collision. Instead of being homogenized, large chunks of it may have sunk, pushed inward by the violence of the impact, settling toward the core mantle boundary because they were denser than the Earth material around them, and once there, insulated by that very density from being stirred back into circulation, they stayed. 4.5 billion years later, they might still be there. 2 continent-sized masses of foreign planetary material, resting quietly at the bottom of the world, beneath the African plate and beneath the Pacific Ocean, slowly influencing the mantle convection above them, and leaving faint chemical fingerprints in the volcanic rocks that rise to the surface thousands of kilometers overhead. If Theia's remnants are anywhere in the solar system, these structures might be where they went. And here's what makes that idea particularly striking in the context of everything we've discussed so far. Remember the isotopic crisis, the fact that the Moon's chemical fingerprint matches Earth's perfectly, with no trace of Theia visible anywhere in the lunar samples? If Theia's material didn't fully mix into Earth's bulk, that would actually help explain part of that mystery. The surface of Earth, the mantle we sample through volcanoes and plate tectonics, would look predominantly like original Earth material, because Theia's contribution got sequestered deep below, out of reach of normal geological cycling. The Moon, built from the debris thrown outward during the impact, would also be dominated by Earth material for the same reasons. The outer layers of both bodies, the ones most easily ejected into orbit, were predominantly Earth's. Theia's denser interior sank rather than flew. The Moon's isotopic identity and the existence of the LLSVPs might not be 2 separate mysteries at all. They might be the same mystery, viewed from different directions. One is orbiting above your head, the other is buried beneath your feet, and both of them are pointing at the same event, the same few hours of chaos 4.5 billion years ago, when a foreign world hit this one and everything changed. Now, it's important to be honest about where the science actually stands on this. The evidence is indirect. No one has sampled the LLSVPs. The seismic anomalies are real and well documented, but the interpretation of what's causing them is still genuinely debated. Other explanations exist, ancient Earth material that differentiated early and never fully remixed, chemical gradients built up over billions of years of geological processing. Some researchers find the Theia hypothesis compelling. Others think it asks too much of structures that have had 4.5 billion years of convection working against their survival. It is a live scientific debate, not a settled conclusion. But here's the thing. The fact that this hypothesis exists at all, that it is being taken seriously, modelled, published in major journals, and actively investigated, tells you something important about where planetary science is right now. We are at a moment where the origin story of the Moon and the deep structure of the Earth are being understood as parts of the same problem, and that problem, it turns out, is far from over. Theia may not have disappeared. It may have just gone very, very deep. Part 9. The Theory That Won't Die Quietly. In 2023, a research team led by Chen Yuan at the California Institute of Technology published a paper proposing something remarkable, that the large low-shear velocity provinces in Earth's mantle might be remnants of Theia, preserved since the giant impact 4.5 billion years ago. Let that sit for a second. Because what that sentence is actually saying is this: the planet that hit us, the foreign world that we have been searching for in lunar rocks, in meteorites, in asteroid belt compositions, finding nothing, may never have left. It didn't scatter into space. It didn't get homogenized into Earth's bulk and disappear into the geological background noise. Parts of it sank. Slowly, under the crushing pressure of everything above them, they settled toward the bottom of the world and stayed there. And they might still be there now, Two continent-sized masses of alien planetary material sitting quietly at the base of Earth's mantle, 4.5 billion years later, waiting for us to figure out what they are. The argument goes roughly like this. When Theia hit Earth, most of the material from the collision was redistributed. Some went into forming the Moon, some was incorporated into Earth's growing bulk, some was lost to space. The collision was not a neat, controlled event. It was chaos at a scale that has no modern equivalent. Two planets, one the size of Mars, colliding at tens of thousands of kilometers per hour, both partially vaporizing, material flying in every direction, the outcome determined by the physics of those first few minutes playing out across the subsequent thousands of years. In that chaos, most things mixed. Rock from Theia and rock from Earth tumbled together, melted together, eventually became indistinguishable from each other in the bulk of the planet that reassembled afterward. But not all of Theia's material would have been perfectly mixed into Earth's mantle. This is the key insight. Theia, as a differentiated planet, had its own mantle with its own chemical composition. It had been a fully formed world, with a core of dense iron at its centre, a mantle of silicate rock surrounding it, and a crust at the surface. The different layers had different densities, different chemical makeups, different fates during the collision. The outer layers, the crust, the upper mantle, were more easily disrupted. They were the parts most likely to be ejected into orbit, eventually contributing to the Moon, or mixed into Earth's upper layers during the violent aftermath. But the deeper, denser portions of Theia's mantle, under certain impact conditions, those may have behaved differently. Rather than being flung outward or stirred upward, they may have been driven inward, pushed deep into Earth's interior by the momentum of the collision itself, sinking toward the core mantle boundary rather than being ejected into orbit or mixed thoroughly into Earth's upper mantle. Theia's mantle material in this scenario would have been denser than Earth's mantle, a difference in composition that could have allowed it to sink rather than mix. Think of it like pouring cold, dense salt water into a tank of warmer, lighter fresh water. The denser fluid sinks and pools at the bottom, rather than dispersing evenly through the tank. Theia's deep mantle material, denser than the Earth rock surrounding it, would have done something similar, settling at the base of Earth's mantle and forming stable accumulations. And these accumulations, insulated by their very density from being stirred back into circulation over billions of years of mantle convection, would still be there today. And they would look like dense, chemically anomalous, seismically distinct structures sitting at the core mantle boundary. They would look, in other words, exactly like the LLS-VPs. This is the moment in the hypothesis where everything clicks into place in a way that is either deeply satisfying or deeply unsettling, depending on how you think about it. Scientists have been staring at those two structures for decades, mapping them with seismic waves, measuring their anomalous densities, finding their strange geochemical fingerprints in the lavas of deep mantle hotspots, and asking the same question over and over, what are you? And the answer that Chen Yuan's team put forward is essentially, they're the other planet. They're what's left of Theia after the rest of it became the Moon. This theory is striking not only because of what it proposes about Earth's interior, but because of what it implies for the Moon formation story. Remember the isotopic crisis, the fact that the Moon's chemical fingerprint matches Earth's with a precision that no standard impact model can explain. The Moon should carry Theia's signature. It carries none. And that has been the central unsolved problem in lunar science for 50 years. If Theia's material didn't fully mix into Earth, if significant portions of it remained as distinct, dense blobs, rather than being homogenized into the bulk mantle, that would help explain why Theia's isotopic signature doesn't dominate Earth's bulk composition either. The material that Theia contributed to the giant impact debris disk, and therefore to the Moon, would have been predominantly Theia's less dense outer layers, which were more easily ejected during the collision. The denser, deeper portions of Theia's mantle might never have fully mixed with Earth's mantle at all. They just went down instead of up. The isotopic picture of Earth's surface, the one that matches the Moon so closely, might therefore be measuring primarily Earth's original material, with the foreign Theia components sequestered in the deep mantle, hidden from surface sampling, preserved in the dark at the base of the planet. The Moon's isotopic identity and the existence of the LLS-VPs stop being two separate mysteries and start being two symptoms of the same event, viewed from different angles. One mystery is orbiting 250,000 miles above your head. The other is buried 2,900 kilometers beneath your feet. Both of them are fingerprints of the same collision. It's an elegant hypothesis. It has real scientific grounding in impact dynamics and mantle density contrasts. And it connects the Moon's isotopic mystery to Earth's deep interior in a way that makes both problems part of the same story. For that reason alone, it deserves to be taken seriously, and it is being taken seriously, modelled, debated, published in major peer-reviewed journals, and actively investigated by some of the best planetary scientists working today. But it comes with important caveats. The evidence is indirect. No one has directly sampled the LLS-VPs. No drill exists that could reach them. No instrument we currently possess can retrieve a piece of that material and put it in a mass spectrometer and tell us definitively what it's made of. Everything we know about these structures comes from seismic waves and from the faint chemical echoes they leave in deep mantle volcanic rocks at the surface. The density and velocity anomalies they display are consistent with the hypothesis, but they do not uniquely confirm it. Other explanations for the same anomalies exist, involving chemical differentiation within Earth's own mantle over billions of years of geological processing, ancient piles of subducted oceanic crust, primordial reservoirs of material from Earth's own earliest history that simply never got stirred back into the system. The geochemistry community is genuinely divided, and reasonable scientists land on different sides of this question. Some researchers find the Theia mantle hypothesis compelling and see it as a productive framework for future investigation. Others remain skeptical, pointing to a fundamental problem that the hypothesis hasn't fully solved: the difficulty of demonstrating that the LLS-VPs have been stable and unmixed for 4.5 billion years in a mantle that has been vigorously convecting throughout that entire time. Mantle convection, the slow, grinding circulation of solid rock driven by temperature differences, operating at timescales of millions to hundreds of millions of years, should, over the full age of Earth, have mixed and homogenized its contents thoroughly. This is not a minor objection. The mantle is not static. It flows, slowly but relentlessly, and that flow has had 4.5 billion years to work with. The fact that the LLS-VPs exist at all as distinct structures is itself somewhat surprising, and suggests either that they formed relatively recently, or that they are exceptionally stable for reasons we don't yet fully understand. Getting a primordial Theia-derived structure to survive that entire timescale requires some explanation for why it wasn't churned up and mixed like everything else around it. The density difference helps. A denser blob resists being stirred into lighter material. But whether that resistance is sufficient to explain 4.5 billion years of survival in an actively convecting mantle is a question the models haven't definitively answered. None of this is fatal to the hypothesis. A crack in the argument is not the same as a collapsed argument, but it illustrates honestly where the science stands right now. Tantalizing, scientifically reasonable, not yet confirmed, and not easily dismissed. Sitting in that uncomfortable zone that the best scientific questions tend to occupy, too compelling to ignore, too uncertain to declare solved. Theia may be sitting underneath us right now, or it may not be. We genuinely don't know, and the tools needed to find out are still being developed, which is one of the most honest and quietly thrilling things you can say about any scientific mystery. It means the answer is still out there. It means the story isn't finished. It means whoever figures this out hasn't been born yet. Or maybe they have, and they're watching this right now. Part 10. A planet built from collision debris. There's a broader idea that the LLS-VP's hypothesis points toward, one that changes how you think about Earth as an object, not just as a scientific object, as the object, the one you live on, the one that produced you. For most of human history, Earth was understood, at least implicitly, as a kind of original creation, something that formed where it is, from local material, and has been here ever since in more or less its current form. This wasn't really a conscious assumption. It was just the default. The ground beneath your feet feels permanent in a way that's hard to argue with. Mountains feel eternal. Oceans feel ancient. The idea that the planet itself, not just its surface, but its fundamental composition, its interior structure, its raw material, could be something other than originally Earth's own, is not an idea that comes naturally to a species that has only existed for a few 100,000 years on a world that is 4.5 billion years old. Geology revealed, slowly and painfully over the last 2 centuries, that the surface has changed dramatically. Continents move, mountains rise and erode and rise again, ocean floors spread outward from mid-ocean ridges and get swallowed back into the mantle at subduction zones. The map of Earth 200 million years ago looks nothing like the map today, and the map 200 million years from now will look nothing like either. The surface is not permanent. The surface is a slow-motion catastrophe that we experience as solid ground because we live at the wrong time scale to perceive the motion. But even as geologists dismantle the idea of a permanent surface the deeper assumption held, the planet itself, the raw material it's made of, was still understood as Earth's own. Formed here, from here, fundamentally ours. The giant impact hypothesis already cracked that assumption by suggesting that Earth's moon came from a foreign body. That was strange enough. The idea that a piece of another world is orbiting us, that the thing lighting up our nights and pulling our oceans into tides is built partly from the wreckage of an alien planet, that already asks something significant of our intuitions about where we live. But it preserved a kind of consolation. The moon came from somewhere else. Earth, at least, was still Earth. The Theia mantle hypothesis removes that consolation entirely, because what it's proposing is not that a piece of Theia became the moon, it's that a piece of Theia became Earth. Specifically, it became the deep interior of Earth, the foundation, the base, the structure sitting underneath everything else. The ground under your feet is not, in this picture, purely the product of Earth's original formation. It is built, at least in part, from the compressed remnants of a world that formed somewhere else and arrived here through violence. Earth, in this view, is not a pure product of its original formation. It is a reprocessed world, a composite, built from at least 2 planetary bodies, and possibly influenced by the debris of many more smaller ones that struck it during that first chaotic 100 million years of solar system history. The giant impact was not just the event that created the moon, it was the event that created the Earth as we know it, fundamentally reshaping its interior structure, its chemical composition, its thermal evolution, possibly even the conditions that allowed plate tectonics to operate the way it does. The world that existed before Theia hit was a different planet than the one we live on, not just scarred or altered, different in kind. This is a philosophical shift as much as a scientific one. It means that when you ask the question, what is Earth made of, the complete answer includes material from at least one other world. You are, in a very literal sense, standing on the compressed remains of a collision between planets. The atoms in the ground beneath you have a more complicated history than Earth alone. Some of them spent tens of millions of years inside a completely different planet, before that planet ceased to exist as a separate object and became part of this one. This fits into a broader picture of planetary formation that has been gaining traction in the last couple of decades, and it's worth stepping back to appreciate how much that picture has changed. The old story was clean. Planets form from a disk of gas and dust surrounding a young star. The dust clumps into pebbles, the pebbles clump into rocks, the rocks clump into planetesimals, the planetesimals grow into planets, each one assembling from the local material available in its orbital neighbourhood, gradually and more or less peacefully settling into its final form, isolated, self-contained, the product of its own local environment. That story is not wrong exactly. The broad strokes are still valid, but the details have been getting messier and messier as our models improve and our samples accumulate. The early solar system was not a peaceful place. The inner solar system in particular was a demolition derby of planet-sized objects crossing each other's orbits, colliding, merging, breaking apart. Material from different orbital distances got mixed together on a massive scale. Large impacts were not rare accidents at the end of planetary formation. They were a fundamental part of the process, happening constantly, reshaping whatever had formed so far and starting the accumulation process again from a different starting point. Earth is not exceptional in this regard. Mars shows geochemical evidence of having experienced large impacts early in its history. The Moon itself, before we even get to how it formed, shows the scars of a period called the Late Heavy Bombardment, when the inner solar system was pelted with impactors on a scale that resurfaced entire worlds. Mercury's enormous iron core, disproportionately large for a planet its size, is most easily explained by a giant impact that stripped away most of its original mantle. Even the outer solar system carries these marks. Many of the moons of the giant planets show evidence of catastrophic early collisions. Violent planetary reshaping is not the exception in solar system history, it is the rule. What's unusual about Earth is not that it experienced these events. Every planet did. What's unusual is the specific outcome of the events Earth experienced, the particular set of consequences that followed from those collisions, which turned out to be, against what seemed like very long odds, profoundly favourable for the emergence of complex life. Think through the chain of consequences that traces back to the giant impact. The Moon formed, and the Moon is large enough to stabilise Earth's axial tilt over geological timescales, preventing the kind of chaotic obliquity variations that would swing Earth's climate between extremes that might have made complex life impossible. Without the Moon, Earth's axis might wander by tens of degrees over millions of years, turning what are now temperate zones into polar wastelands and back again on timescales too fast for evolution to track. The Moon's gravitational steadying hand may have been a prerequisite for the long-term climate stability that allowed complex ecosystems to develop. The tidal forces generated by the Moon in Earth's early oceans may have created the kinds of dynamic, chemically rich tidal zone environments where some researchers believe the first self-replicating chemistry emerged. The energy input from lunar tides into Earth's interior may have influenced the planet's geological activity in ways still being worked out. And then there are the LLSVPs themselves. If they are Theia remnants, they have been sitting at the base of the mantle for 4.5 billion years, anchoring the pattern of mantle convection, channeling deep mantle plumes to specific locations, influencing where volcanic hotspots appear at the surface, and therefore influencing the long-term pattern of atmospheric chemistry, ocean circulation, and continental distribution that has shaped the history of life on this planet. The location of Hawaii is not random. The volcanism of Iceland is not random. If the structures driving those deep mantle plumes have been in place since the giant impact, then Theia has been quietly shaping the geography of life on Earth for its entire history. The collision that should have been catastrophic may have been foundational. A Mars-sized planet hitting the early Earth at the right angle, at the right speed, with the right energy, and the result was not the destruction of a world but the creation of a better one. Theia didn't end Earth. Depending on how you look at it, Theia completed it, gave it a moon to steady its spin, buried structures in its interior that may have driven the geological dynamism that kept the planet habitable, and set in motion the specific chain of consequences that led, 4.5 billion years later, to a species capable of looking up at the Moon and asking where it came from. That is either a remarkable coincidence or evidence of something deeper about the conditions that produce habitable worlds, and science does not yet know which. What it does know is that the consequences of that ancient collision are not confined to history. They are still unfolding. The LLSVPs are still there. The mantle is still moving around them. The plumes they generate are still feeding volcanoes at the surface. The Moon is still steadying our axis, still pulling our tides, still doing the quiet work that makes this planet livable. We are not just descended from stardust, as the poetic version of the story goes. We are descended from a collision, from wreckage, from the specific, improbable outcome of two planets meeting at exactly the wrong moment in exactly the right way. And somehow, impossibly, it worked out. Part 11. The Hidden Geological Consequence. The mantle is not static. Despite being made of solid rock, and it is solid, not liquid, despite what many people assume, it flows. This is one of those facts about Earth that sounds wrong the first time you hear it, and then slowly becomes one of the most fascinating things you know. Rock, solid rock, flowing, not melting, not becoming liquid, just moving. Deforming under pressure and heat over timescales so vast that the word slow doesn't really capture it. We need a different word, something that means slow the way geology means slow, which is to say, imperceptibly, relentlessly, and without any concern whatsoever for the span of a human life, or a human civilization, or even a human species. At the temperatures and pressures that exist hundreds of kilometers below the surface, rock behaves plastically over geological timescales. The distinction between solid and liquid starts to blur at those conditions, not because the rock melts, but because the crystal structures within it can deform and flow given enough time and enough pressure. What would take millions of years to move even a centimetre under normal surface conditions flows, very slowly, under the conditions of the deep mantle. A piece of mantle rock might take 100 million years to complete one full circuit of the convection cell it's caught in. From a human perspective, it isn't moving at all. From a geological perspective, it's churning. This process is called mantle convection, and it is ultimately what drives plate tectonics on Earth's surface. And plate tectonics, in turn, is arguably the single most important geological process for making Earth the kind of planet it is, recycling carbon back into the atmosphere through volcanic outgassing, regulating the long-term climate through the drawdown of carbon dioxide by weathering and its return through volcanism, creating the chemical diversity of environments across different rock types and ocean chemistries that may have been essential for the emergence and diversification of life. Take away plate tectonics, and Earth probably looks a lot more like Venus, geologically stagnant, surface temperature hot enough to melt lead, atmosphere thick with carbon dioxide that has nowhere to go. Plate tectonics is not just interesting geology. It may be a prerequisite for a planet like ours to exist, and plate tectonics is not driven from above. This is the part that surprises people. The movement of the large crustal plates that carry the continents and ocean floors is not something that happens at the surface and propagates downward. It's driven from below. The surface expression of plates moving, the earthquakes, the volcanoes, the slow drift of continents across the face of the planet is a consequence of the convection patterns in the mantle beneath them. Hot material rises in some places, cooler, denser material sinks in others, and the circulation that results drags the surface plates along with it, like debris on the surface of a slowly boiling pot. The continents are passengers. The mantle is the engine, which means that anything influencing the pattern of mantle convection is, indirectly, influencing everything above it. The distribution of continents, the location of mountain ranges, the pattern of ocean basins, the history of climate. All of it flows ultimately from what's happening in the mantle, and the mantle's behaviour is shaped, in part, by what's sitting at its base. The large low shear velocity provinces sitting at the base of the mantle are not passive observers of this process. They appear to influence mantle flow in significant ways, and the evidence for this is visible at the surface if you know what to look for. Hot plumes of mantle material, columns of relatively buoyant superheated rock that rise from the base of the mantle all the way to the surface, are the structures responsible for what geologists call hotspot volcanism. Hawaii is a hotspot. The Canary Islands are a hotspot. Iceland sits on a hotspot. These are places where volcanic activity occurs not because two tectonic plates are colliding or separating, but because a column of unusually hot material rising from the deep mantle is punching through the overlying plate from below, feeding magma to the surface independently of the plate boundary system. And those plumes, those deep mantle columns of rising hot rock, appear to be preferentially located at the edges of the LLSVPs, not randomly distributed across the base of the mantle, but clustering around the margins of these two enormous structures, as though the structures are organising the upwelling. The LLSVPs seem to act as anchors or sources for these plumes, channeling the upwelling of hot material in specific geographic patterns that have remained, at least broadly, consistent over geological time. Hawaii has been sitting over its hotspot for tens of millions of years, producing a chain of volcanic islands and seamounts that stretches across the Pacific as the plate above it moves while the plume stays fixed below. The plume is fixed because whatever is generating it at the base of the mantle, the edge of the Pacific LLSVP, has been in roughly the same place for a very long time. Now extend that backward in time. If the LLSVPs are truly primordial structures, whether they are Theia remnants or ancient Earth material that differentiated early and never remixed, then their influence on mantle convection is not a recent phenomenon. They have been sitting at the base of the mantle, organising plume activity, anchoring convection patterns, shaping the flow of the engine that drives everything above them, for potentially the entire history of the planet. 4.5 billion years of mantle convection, influenced throughout by structures that may have been put in place in the first hours after the giant impact. Follow that chain of consequence forward, and it becomes genuinely vertiginous. The pattern of mantle convection over Earth's history determined how the plates moved. How the plates moved determined how the continents assembled and broke apart, from the first supercontinent to Pangaea to the current configuration. How the continents were distributed determined ocean circulation patterns, which regulated climate, which shaped the environments available for life to colonize. The locations of volcanic hotspots determined where and when large volcanic provinces erupted, releasing gases into the atmosphere that altered its composition, sometimes catastrophically, sometimes in ways that opened new ecological possibilities. The entire geological narrative of this planet, the 4.5 billion year story of a world becoming habitable and then inhabited, was being written, at least in part, by two continent-sized structures resting at the base of the mantle. A collision 4.5 billion years ago may have determined where Africa is today. Let that land for a moment. Not metaphorically, literally. The current position of the African continent sitting above one of the two LLSVPs may be connected to the presence of that structure beneath it, because the LLSVP influences the convection pattern above it, and the convection pattern influences how the plates above that move, and the plates carry the continents. The same logic applies to the Pacific. The same logic applies, in cascading ways, to everything that has happened on this planet's surface since the beginning. It may have influenced the pattern of volcanic activity that shaped the atmosphere over geological time, the Great Oxygenation Event, the Snowball Earth episodes, the mass extinctions driven by flood basalt volcanism, all of these tied in complex ways to the long-term behaviour of the mantle and the deep structures governing it. It may have affected the habitability of Earth in ways too complex to fully trace, in causal chains too long and too branching for any model to follow completely. But the influence was real, and it was continuous, and it has never stopped. The moon-forming impact is not just ancient history, sealed off from the present by the passage of billions of years. It is not a completed event with a fixed outcome that we merely need to discover and record. If the LLSVPs are what some scientists think they are, that impact is still shaping the planet in real time, right now, today, in the movement of the plates and the eruption of volcanoes and the slow drift of continents that is still happening beneath our feet at this very moment. We are, in a very real sense, still living in the aftermath of the collision. The aftershocks, measured in geological time rather than seconds, are still propagating through the system. The event is not over. It has just slowed down to a speed we cannot perceive. This is either deeply unsettling or deeply fascinating depending on your disposition. Probably both, simultaneously. In the way that the best scientific revelations tend to be, the ones that make the familiar strange and the strange somehow more intimate than the familiar ever was. And it underscores why the moon's origin story matters, not just as a question of historical curiosity, not just as a puzzle for specialists to argue over in academic journals, but as a question with direct consequences for understanding the Earth we live on, right now, in the present. The moon overhead and the mantle below are not separate topics. They are the same topic. They are the same event, still unfolding, still leaving its mark on a planet that would not exist in its current form without it. The answers to that story are written in two places. In the deep mantle beneath our feet, which we cannot easily access, not yet, not with any tool we currently possess, and in the ancient rocks on the surface of the moon, which we can. Rocks that have been sitting undisturbed for 4 billion years, preserving a chemical record of the event that created them, waiting with the patience of objects that have no concept of waiting for someone to come and read what they contain. And right now, for the first time in more than 50 years, we're going back to do exactly that. The question that the Apollo missions uncovered is still open. The tools to answer it are finally catching up, and the rocks are still there, exactly where the moon left them. Part 12. The Return to the Moon. In December of 2023, something happened that hadn't occurred in more than half a century of human space exploration. For the first time since Eugene Cernan climbed back into the lunar module during the final Apollo mission in December 1972, humanity once again pushed beyond Earth orbit with the moon as its destination. This time, it wasn't a landing mission, and it wasn't designed to repeat Apollo's footsteps. It was something quieter, more deliberate, and in some ways more ambitious. The mission, Artemis II, carried 4 astronauts on a carefully plotted trajectory around the moon, before returning them safely to Earth. They never touched the lunar surface. They didn't collect rocks. They didn't deploy instruments. But what they did do was symbolic and scientific in equal measure. They reopened the door to deep lunar exploration after an entire generation of absence. Artemis II marked the beginning of NASA's renewed lunar program, a long-term effort not just to revisit the moon, but to fundamentally re-examine what the moon is, where it came from, and why it still holds unanswered questions about Earth's earliest history. In that sense, it wasn't just a mission, it was a reset point. A signal that the moon was once again central to the biggest unresolved problem in planetary science. To understand why this matters, you have to understand how different Artemis is from Apollo. Apollo was a product of urgency, competition, and exploration. The goal was to land humans on the moon and return them safely. The science that came out of it was extraordinary, but it was never the primary mission objective. Astronauts collected samples where they could land safely, flat regions near the lunar equator, often in volcanic plains formed later in lunar history. Those samples reshaped planetary science forever, revealing the moon's volcanic past, its age, and its internal structure. But they were geographically limited. They represented only a thin slice of the moon's full geological story. Artemis is designed to correct that limitation. Instead of focusing on accessibility, Artemis is targeting scientific value. One of its primary destinations is the lunar South Pole, a region unlike anything explored during Apollo. Here, sunlight barely grazes the horizon, leaving deep craters in permanent shadow for billions of years. In these cold traps, scientists believe water ice may have accumulated and survived untouched since ancient times. Even more importantly, the surrounding terrain may contain some of the oldest exposed material on the moon's surface, rocks that predate most volcanic activity, and may preserve a record of the moon's earliest crust. Then there's the far side of the moon, eternally hidden from Earth due to tidal locking. It is not simply the back of the moon, it is geologically distinct. The crust is thicker, the volcanic plains are sparse. The surface appears more heavily scarred and in many regions older in appearance than the familiar near side. Some researchers believe the far side may preserve a more complete and less altered record of the Moon's earliest formation, potentially holding clues that the more volcanically resurfaced near side has erased. And it is precisely here, on these ancient untouched regions, that the Moon's biggest mystery becomes scientifically testable. At the centre of the lunar origin problem is a simple but deeply unsettling observation. The Moon and Earth are chemically almost identical in key isotopic systems. Oxygen isotopes, titanium ratios, chromium signatures, tungsten distributions, all of these act like planetary fingerprints. Across the solar system, these fingerprints are usually distinct. Mars has its own signature. Meteorites from different parent bodies show clear variation. Even asteroids from the same general region of space can be chemically separated with high precision. But the Moon does not behave this way. It mirrors Earth with a precision that is difficult to reconcile with standard formation models. Apollo-era measurements first revealed this similarity, but those measurements were limited in scope. They came from a relatively small number of locations, mostly lunar mare basalts, dark volcanic plains that formed after the Moon's early history had already played out. These regions are scientifically valuable, but they are not representative of the Moon's deepest or oldest crust. This is where Artemis becomes scientifically transformative. The isotopic mystery at the heart of the Moon's origin story cannot be resolved with partial sampling. It requires access to the oldest lunar material, the highland crust, deep impact excavations, and polar regions where ancient rock may have been preserved without being melted, mixed, or resurfaced by volcanic activity. Only by sampling across these regions can scientists determine whether the Earth-like isotopic signature is universal across the Moon or confined to specific layers formed after its birth. In parallel, measurement technology has advanced dramatically since the Apollo era. The instruments used in the 1970s were groundbreaking for their time, but modern mass spectrometers now operate with sensitivity levels that would have been unimaginable back then. They can detect isotopic differences at far smaller scales, revealing subtle variations that were previously hidden in measurement noise. This means that even if the Moon and Earth are not perfectly identical, we may now finally be able to detect where and how they diverge. Small deviations could reveal whether the Moon formed from a fully mixed vapor disk, a partial impact blend, or a more complex sequence of events involving multiple stages of accretion and reprocessing. The stakes are higher than they first appear. The Moon is not just a passive companion orbiting Earth. It is the most complete and accessible record of Earth's earliest catastrophic history. Unlike Earth, which has been reshaped continuously by plate tectonics, erosion, and recycling of its crust, the Moon has preserved its ancient surface with minimal alteration for billions of years. It is, in effect, a geological archive, one that contains information about a period of time on Earth that no direct rock record can preserve. This is why lunar exploration is not just about space science, it is about planetary forensics. The Moon holds evidence of the single most important event in Earth's formation history, and possibly one of the most important events in the entire inner solar system. If the giant impact hypothesis is correct, then the Moon is the physical remnant of a planetary-scale collision that fundamentally reshaped Earth itself. But the details of that collision, its exact energy, angle, composition, and aftermath, remain uncertain because the evidence does not yet fully align with the simplest models. That is where Artemis's true scientific mission begins. But the challenge is not just about going to the Moon. It is about knowing where to look once you arrive. The samples that could resolve the isotopic mystery are not evenly distributed across the lunar surface. They are concentrated in specific geological contexts, ancient highland terrains formed during the Moon's earliest crustal solidification, deep crater walls where impacts have excavated material from below the surface, and polar regions where extreme cold may have preserved volatile compounds and primitive rock structures unchanged since their formation. Finding these materials is not a matter of chance. It requires a detailed understanding of lunar geology, impact excavation processes, and crustal evolution over billions of years. Because hidden within those rocks may be the final missing piece of the moon's origin story. A piece that could confirm whether the moon truly formed from a chaotic planetary collision, or whether something far more complex happened during the earliest moments of Earth's history, something we are only now beginning to have the tools to understand. Part 13. The oldest rocks hold the secret. The moon has no plate tectonics, no shifting crust slowly recycling itself back into the interior. No atmosphere to drive wind, weather, or erosion. No rain-carving valleys or rivers transporting sediments across continents. No oceans cycling minerals through endless chemical exchange. On Earth, all of these processes constantly erase the past, crushing it, melting it, subducting it, or burying it under newer layers of rock. The moon is the opposite of that system entirely. What exists on its surface today has, in many cases, remained almost exactly where it formed for billions of years. Impact craters still sit where they were blasted into existence. Ancient lava plains are still frozen in place. Dust layers have accumulated slowly over eons, but they do not erase what lies beneath. They merely sit on top of it like a thin, patient blanket. In geological terms, the moon is not an active world. It is a preserved one. That difference is everything. Earth behaves like a living machine, constantly rewriting its own history. The moon behaves like a sealed archive, storing its earliest chapters without revision. Because of that, Earth has lost almost all of its original crust from the first few 100 million years of its existence. Plate tectonics has destroyed, melted and recycled nearly every rock that could have told us what the early Earth looked like. The deepest time in Earth's history is largely inferred, not directly observed. The moon, however, did not participate in that cycle. It preserved it, and the most important preserved record lies in the lunar highlands. These highlands are the pale, heavily cratered regions that dominate much of the moon's surface, especially across the far side. From orbit, they look almost ancient even at a glance, lighter in colour than the dark volcanic plains known as Maria, and densely scarred by impacts that overlap like layers of memory stacked on top of each other. Geologically, these highlands are not just old, they are primordial. They are composed primarily of a rock type called anorthosite. This is a light-coloured igneous rock rich in feldspar, formed under very specific conditions. To understand why that matters, you have to go back to the earliest phase of the moon's existence, when it was not yet a cold, solid body, but something far more extreme. In the leading model, the young moon began as a global magma ocean. After its formation, the entire body was so hot that much of its outer layer existed in a molten or partially molten state. Over time, as it cooled, minerals began to crystallize out of this magma ocean in a predictable sequence based on their density. The key mineral here is feldspar. Feldspar is relatively light compared to other silicate minerals. As the lunar magma ocean cooled, feldspar crystals formed and floated upward, accumulating at the surface like foam rising to the top of a boiling liquid. Over time, this floating layer solidified into a global crust composed largely of anorthosite. That crust became the lunar highlands we see today. This is why the highlands are so scientifically important. They are not just ancient terrain, they are the frozen product of the moon's first major geological event after its formation. In a sense, they are the moon's original skin. And because they formed so early, roughly 4 to 4.5 billion years ago, they are among the oldest intact geological materials in the entire solar system. This is where the moon's origin story becomes more than just a theoretical model and turns into something testable. If the moon formed from a mixture of Earth and Theia material, then that mixture should have been present in the magma ocean itself. And if that is true, then the crystallizing minerals of the early moon should have recorded that mixture at the chemical and isotopic level as they formed. In other words, the anorthosites are not just rocks. They are chemical snapshots of the moon's birth environment. They crystallized directly from the first-generation magma ocean, before later volcanic activity reshaped the surface, and before billions of years of impacts churned and mixed the outer layers. If any part of the Moon still preserves a clean record of its original composition, it is these ancient highland rocks. So if Theia contributed material to the Moon, or if Earth and Theia were chemically blended during the impact, traces of that process might still exist here, locked into mineral structures at levels so subtle that early instruments simply could not detect them. This is where modern science re-enters the story. During the Apollo missions, astronauts did in fact collect samples of highland material. One of the most famous is the so-called Genesis rock, collected during Apollo 15. This sample is a piece of ancient anorthosite crust, dated to approximately 4.1 billion years old. When it was first analysed, it offered a direct glimpse into the Moon's earliest crust-forming processes. But there is a limitation that becomes increasingly important the deeper you go into this mystery: sampling bias. The Apollo missions landed on the near side of the Moon, in regions that were safe for landing and relatively smooth. These areas, while scientifically valuable, are not necessarily representative of the Moon's oldest or most undisturbed crust. They are also heavily influenced by billions of years of meteorite impacts that have continuously churned the surface, mixing materials from different depths and different eras. This creates a problem for the isotopic question. Even if the Moon's original crust contained subtle variations in composition, impact mixing could have blurred or partially erased those signals in the samples we already have. The near-side highlands, in particular, have been repeatedly reworked by large impact events and ejecta redistribution, meaning they are not pristine archives, they are edited ones. To access a more faithful record of the Moon's earliest composition, scientists need to look elsewhere. One of the most important targets is the lunar South Pole, especially the interior of the South Pole Aitken Basin. This structure is not just another crater. It is the largest confirmed impact basin in the solar system, stretching roughly 2,500 kilometers across the Moon's far side, and reaching depths of about 8 kilometers. Its formation was so energetic that it likely penetrated deep into the lunar crust, and possibly into the upper mantle. That matters because it turns the basin into a natural excavation site. Unlike surface regions that only reflect the uppermost crust, the South Pole Aitken Basin may expose material that originated far below the surface, material that has been shielded from billions of years of surface mixing. If there are any compositional differences between the Moon's deep interior and its outer crust, this is one of the few places where that contrast might be visible. In the context of the Moon's origin story, that is critical. If the Moon formed from a fully mixed Earth-Theia system, then the isotopic signature should be consistent throughout its interior. But if the mixing was incomplete, or if later processes altered only the surface layers, then deeper material might preserve a slightly different record. That is exactly what scientists are trying to test. Modern radiometric dating techniques also add another layer of precision to this investigation. Compared to the technology available during Apollo, today's methods can date individual mineral grains within rocks, with uncertainties on the order of just a few million years. That level of precision may sound small in human terms, but in planetary science, it is the difference between reconstructing a vague timeline and resolving a detailed sequence of events across hundreds of millions of years. With improved dating, scientists can begin to map the Moon's early history with much finer resolution, identifying when major crust formation occurred, when volcanic activity peaked, and how long it took for the lunar magma ocean to fully solidify. That timeline in turn constrains the conditions of the giant impact itself. Because the Moon is not just a passive object in this story. It is a record keeper. Every rock on its surface is a frozen fragment of a specific moment in lunar history. Some record the earliest crystallization of the magma ocean. Others preserve the scars of massive impact events that reshaped the surface. Others still contain chemical signatures locked in place since the Moon's first few 100 million years. Taken together, these rocks form a kind of planetary archive, one that has been waiting for billions of years to be read properly. And the most important part is this: we now have the tools to read it. High-precision isotope measurements, advanced orbital mapping, improved sample return missions, and planned Artemis-era exploration all converge on the same goal. Not just to visit the moon again, but to extract information from it that was previously inaccessible. Because the question at the centre of this entire story is still unresolved. Was the moon formed from a chaotic collision that thoroughly mixed two worlds into one? Or is its Earth-like chemistry telling us something deeper about how planets form in the first place, something that current models still cannot fully explain? The rocks are still there, the record still exists, and for the first time since Apollo, humanity is preparing to go back and read it properly. Part 14. The final unresolved question. If you zoom out far enough, the moon stops looking like a simple satellite and starts looking like a forensic archive that was never meant to survive this long. Not a decorative companion to Earth, not a poetic nightlight in the sky, but a locked vault holding the earliest pages of a story we are still trying to reconstruct. The strange part is that we don't lack data. We have a lot of it. What we lack is agreement on how all the data fits together. Think of it like finding a burned manuscript where most of the pages survived, but they were written in overlapping ink from different pens, and the author kept revising the same paragraph under different lighting conditions. That is what the moon's origin problem feels like today. The structure of the story is visible, but the sequence, the mechanism, and even some of the characters remain uncertain. At the centre of this uncertainty is a tension that refuses to go away. The moon looks simple on the outside, geologically quiet, airless, static, but its chemistry tells a story of violence, mixing, heat, and near-total transformation. The giant impact framework captures that violence better than anything else we've ever proposed. It explains why the moon is iron-poor, why it shares angular momentum with Earth, and why its bulk structure is so distinct from typical planetary formation outcomes. But once you move from the broad strokes into the fine details, the simplicity collapses. The biggest crack in the model isn't dramatic shape or orbital mechanics, it's chemistry. Specifically the isotopic fingerprint problem. On paper, a catastrophic collision between two different planetary bodies should produce a moon that reflects a mixture. Part Earth, part impactor, each contributing its own chemical accent. Instead, what we observe is closer to a perfect match, so close that it looks less like blending and more like identity. That's where the discomfort begins, because physics doesn't naturally produce that kind of precision without either extreme conditions or missing steps in our understanding. To make the moon and Earth so isotopically similar, something in the system had to push material into a state of near-total homogenization. That could mean a post-impact disk so energetic it vaporized and remixed everything repeatedly. It could mean multiple impacts over time, each erasing earlier chemical distinctions. It could even mean something more subtle, that the early building blocks of planets in our region of the solar system were already far more chemically uniform than we assumed. Each option solves part of the problem while introducing new complications. It's like adjusting a recipe where fixing the taste breaks the texture. And this is where newer ideas enter the conversation, not as replacements for the giant impact, but as refinements that try to stretch it into something that can actually match the evidence. High-energy synestia-like states, for example, propose that the Earth-Moon system may have briefly existed as a shared vaporized structure, not a planet and a disk, but a continuous rotating mass of rock vapor. In that environment, separation between Earth and Moon becomes less like two bodies forming, and more like one system cooling into two regions. In that scenario, isotopic blending becomes less surprising. It becomes inevitable. Then there's the multiple impact hypothesis, which replaces a single catastrophic event with a sequence of smaller collisions. Instead of one perfect storm, you get repeated strikes, each one partially resetting the system, each one contributing heat, angular momentum, and material mixing. Over time, the moon emerges not from a single moment, but from a process, a slow convergence shaped by repeated violence. Neither model fully wins. Both fit parts of the evidence. Neither explains everything cleanly. Meanwhile, deeper inside Earth, another piece of the puzzle quietly sits in the background. the large low shear velocity provinces at the base of the mantle. These vast dense structures are not directly observable in a conventional sense, but seismic data reveals their presence. They are chemically distinct, unusually stable, and massive enough to reshape how heat moves through Earth's interior. Some interpretations suggest they could be remnants of the early impactor material, a kind of gravitational sediment from the moon-forming event that never fully mixed back into the mantle. Others see them as ancient Earth reservoirs, preserved since the planet's earliest differentiation. Either way, they complicate the story. Because if the moon-forming impact was truly global in its effects, then its fingerprints should not be limited to the sky. They should be embedded deep within Earth itself, still influencing how our planet behaves billions of years later. Now step back up to the surface again, to the moon, because this is where the story becomes even more interesting. The reason scientists are so focused on returning isn't nostalgia or exploration for its own sake, it's precision. Apollo gave us a first look, but it was like studying an ancient civilization through artifacts found only in one city district. Valuable, transformative, but incomplete. The moon's far side, its polar regions and especially its deep impact basins are fundamentally different geological environments. The South Pole Aitken Basin, for instance, is not just a crater, it is a window into depth. A scar so large that it likely excavated material from the moon's lower crust or even mantle. If any region can preserve chemical signatures closer to the moon's earliest internal structure, it is there. This is where modern instrumentation changes everything. Today's mass spectrometers can detect isotopic differences at levels that were simply invisible half a century ago. What once looked identical can now be resolved into subtle gradients. What once appeared uniform may reveal hidden structure. It's similar to upgrading from a blurred photograph to a high-resolution scan. The subject doesn't change, but your understanding of it does. And this is the quiet reason the moon still matters so much scientifically. It is not just a relic. It is a controlled experiment that nature has been running for 4.5 billion years, with no atmosphere to blur the results, no tectonics to recycle them, and no oceans to erase them. Every crater is a timestamp. Every exposed rock is a fragment of early history, preserved almost exactly as it formed. But even with better tools and better targets, the uncertainty remains stubborn. Because the real problem is not just missing data, it is that multiple coherent stories can still be told using the same evidence. One in which the moon is a near-perfect blend of Earth and impactor, another in which it is mostly Earth, reshaped by extreme vaporization, another in which repeated impacts gradually built the system we see today. All of them work, none of them fully closes the loop. So the honest position, the one that survives all the models, simulations and debates, is not certainty, but controlled incompleteness. We know the moon formed from a catastrophic event. We know that event reshaped Earth in fundamental ways. We know the outcome produced a stable Earth-Moon system that may have been crucial for life as we know it. But the detailed mechanics of how raw chaos became a chemically precise system remain unresolved, and that gap matters more than it might seem because it connects directly to something much larger than lunar science. It connects to planetary formation in general. If we misunderstand how our own moon formed, we risk misunderstanding how common systems like it are across the galaxy. Are large moons rare accidents? Or are they natural outcomes of planet formation under the right conditions? That question feeds directly into how we estimate the likelihood of Earth-like worlds elsewhere. Which brings the story back to where it quietly began, with a simple observational paradox that refuses to go away. Earth and Moon are either the result of an extraordinarily fine-tuned cosmic accident, or they are the product of a process we do not yet fully understand. And that is why the next era of lunar exploration matters so much. Not because it will necessarily solve the moon in a single breakthrough, but because it will finally allow us to test the weakest parts of every competing model with data that is precise enough to matter. A far-side anorthosite sample, a deep basin mantle fragment, a polar ice-trapped record of early solar system chemistry. Each one is a potential constraint, a way of narrowing the space of possible histories. In the end, the Moon is not withholding its secrets. It is simply older than our methods of reading it. We built the first language for interpreting its rocks during Apollo. Now we are building a second language, more sensitive, more precise, more aware of how much we still don't know. And that is where the story stands. Not unfinished because we have failed, but unfinished because the object we are studying is still richer than the tools we brought to it the first time around. The Moon is still there, still orbiting, still carrying the record of an event that shaped everything around it. And somewhere in those ancient rocks, in a grain of anorthosite, in a fragment of excavated mantle, in an isotopic ratio just slightly off from expectation, the next chapter of the story is waiting to be read.